great way of distinguishing them. But I'll turn it over to James.
Thanks, Aaron. So now we're going to hear from James Kirk. Go ahead, James.
I need to unmute myself, and I will add my video. Okay, hello. My name is James Kirk, and I will be presenting work on my thesis, which I did back in September. Can everyone hear me? Peter, I guess you can.
Yes, we're hearing you and seeing you. Your voice is breaking up just a little bit. But.
Oh, all right. My internet is good, so hopefully it should be fine. So yeah, so I will be presenting work on my thesis from September. And so that is on learning hierarchical compositional task definitions through online situated interactive language instruction. I graduated, I defended back in September and graduated that year, but now I'm back in Ann Arbor working at Sortec as a research scientist. So kind of the motivating question for this work is how can an intelligent agent learn a novel task? And so I'm going to kind of flip that question on you. I guess we'll be rhetorical in this situation, but how did you learn the rules of a new game? And so I would say, at least for a lot of games that you learned them through situated interactive instruction. So you were sat down with someone that knew the game, possibly your parent, where they're going to interactively teach you the game, where this might involve using language to describe rules, demonstrating moves, but a really kind of interactive instruction that really relies on that you're situated in the same example. And this is about learning kind of the rules of the game rather than about trying to learn a mastery of the game. So the big picture of this research problem is in a shared environment, and you can see a top-down view of a robotic arm that is learning to play tic-tac-toe with these red blocks. So in a shared environment, the teacher describes the task with language. So you can move a free red piece onto a clear location. The goal is that, so on. The question is, how can an agent learn to understand and solve the task in this given context? So this research area, which has already been talked about some by John and Aaron, this is also work done on the ROSI project. So this research area that we're pushing is interactive task learning. So by interactive, we mean real time, fast with few examples, often one shot. We're only giving a single example, basically through language description. It's natural, so that's using language demonstrations. Situated in a shared environment. By task, we mean that it's learning the problem formulation or definition. So these are the actions, goals, etc. of the task. And so we're learning also. So that means that we're acquiring all the knowledge necessary to understand, solve, and perform the task. This doesn't include non-task specific primitives about, simple movements that the agent might have, or colors, for example, like red. So what we're not doing, at least in my case, so this is not the case for Aaron, but in my case, we're not learning a policy or a procedure for the task. We're really focused on learning the structure of the task, so the goals and actions. We're not programmed to handle new task conditions and situations, and we're not using offline batch processing. So this work specifically focuses on learning games and puzzles, which present a large variety of goal-oriented puzzles, which is what we will be learning. And so we're going to learn a problem space formulation. So that's as defined by Alan Newell, actually, a set of initial states, final states, actions over those states, and failure states. And so we're going to learn this problem space through conditional descriptions of all the elements of the problem space, which we're going to call the task elements. So these task elements are the goals, such as the goal is that there are 5 matching locations. Actions, you can move a red block onto a clear location, or failure conditions. If a block is larger than the object it is on, then you lose. So I'm going to take a quick break here and show you guys a quick video where we're teaching paraphernalia. We're going to be using blocks and the tabletop arm instead of discs and pillars that you're used to, but still worried about the relative size of blocks. hopefully the audio will work okay.
The name of the game is Tower of Hanoi.
Okay, what are the actions and goals of the game?
You can move a clear block onto a clear object that is larger than the block.
I don't know the concept clear.
If a block is not below an object, then it is clear.
Okay, I now understand the concept clear. I have learned the action.
The goal is that a large block is on a right location, and a medium block is on the large block, and a small block is on the medium block.
I have learned the goal.
Done.
So everything else was in real time, but here we're speeding it up just as we're showing the solution. But you can see that very quickly it learned the goal of the task, which it didn't know before, the action and the constraints on the action, that it can't place it on a smaller block. And then it's able to solve the puzzle. You might have noticed that we've learned a term that it didn't know, which was clear. So there's a lot of characteristics of this problem that make learning difficult. There's a lack of common ground between the human instructor and the agent. So the human instructor might look at this board where we've got blocks and say, okay, that's a red piece, but in the agent's representation, which the person doesn't have access to, it might see a red block. So there's kind of a disconnect. And this could be a much wider disconnect than just a single term being different. A lot of the concepts that we're learning are compositional. So in the example, the goal is that 5 locations are captured. The definition of captured might be a composition of other concepts. We know that, oh, that captured means that it's below a block and the block is red. We are interested in situations where we're not just learning a single game, but we're learning many games in succession. And so we're concerned with how knowledge accumulates over time, and in particular, how knowledge transfers between similar games. Where we would even expect a little bit of transfer between 5 puzzle and tic-tac-toe because they're both moving around blocks, but we would expect more transfer from tic-tac-toe to another version of tic-tac-toe with marking X's and O's. They share a lot of concepts, even though the domains are different. There's also a many-to-many possible mappings between terms and meanings. So a term like clear could mean that it's transparent, or it could mean that something is not covered. Similarly, empty could also mean that it's not covered, or it could mean that it's not filled, like in that example tic-tac-toe where we're marking values instead of moving pieces. And so I'm going to quickly go through some of the meat of some of the structures that we learn that helps us address some of these problem characteristics. This is a very simple, similar goal example to what you just heard in the Tower of Hanoi video, where we're saying the goal is that a small block is on a medium block and a large block is below the medium block. And so from this, we extract a predicate representation that you can see over here. So where we have different arguments, x1, x2, and x3, and different predicate tests like small block and binary predicate tests like on. From this, we learn a graphical structure, which we have represented here, that helps us minimize computation and also will be very useful for doing hierarchical compositions and transfer of knowledge. This structure we resolve bottom up. So if you look on this view, we have the world. We've given indexes to these objects. So we have blocks A through C and locations X, Y, and Z. So when we evaluate the structure that we learned to see if we can detect the goal, we resolve it from bottom up. So the 6 objects, A, B, and C, are all the blocks. We'll evaluate small, large, and medium, and finally be able to see that yes, this goal can be satisfied with the current situation that we see.
James,
A more complicated
James?
example. Yep.
Sorry to interrupt, but your voice is breaking up a lot. Maybe you could mute your video. It might help.
My video is closed. I'll try to be closer to my
I can
video.
mute it for you.
okay.
Okay, go ahead.
Is that better?
No, but
Can you hear me?
Yeah, go ahead. Keep talking.
Maybe not.
Just go ahead, James. We'll do our best.
Hello?
Yes, we hear you. We hear you. Go ahead.
Okay, can you hear me now? Yeah, it looks like I'm unmuted.
Yes, we hear you. Go ahead with your talk.
Peter?
Yes, we're hearing you. Sorry,
Okay,
James.
I'm going to continue.
Just go ahead with your
I
talk.
have not heard from Peter, but all right. So, oh, I guess I can't hear you guys. I muted my speakers. Sorry for the confusion. So, sorry about that. We're back. So this is a more complicated example where we're learning the goal of tic-tac-toe. And so here on the side, we have a representation of tic-tac-toe where we've got locations with indexes and objects that are ID'd 1 through 16. We're being taught the goal of tic-tac-toe. So the goal is that 3 of the captured locations are in a line. And here it builds a structure, but it can't resolve captured. So it asks for a definition for captured. And so we say if a location is below a red block, then the location is captured. But you'll notice here that it also, so we're highlighting in red just to indicate that we aren't able to resolve this part of the structure. And so what we'll do is we'll recursively ask for definitions until we can resolve this structure. And so we'll ask for definition for below. So in this case, the agent actually didn't have representation of below, so we need to teach it by using on and saying, oh, if a block is on a location, then the location is below the block. And this way we can recursively learn this entire structure. So here is another example with frogs and toads. And so we're teaching an action where this is a hopping puzzle where you're trying to hop all the frogs over the toads and have them swap sides. So an action description would be if a toad is to the right of a clear location, then you can move the toad onto the location. But in this scenario, we're saying that we've already learned 2 different definitions for clear. So again, a big part of this is just transferring knowledge. So how do we handle this? So what we do is we will create multiple interpretations if we have multiple definitions for concepts. And then we can do some analysis and even some possible further interaction to clarify which is the correct version, whether it's clear where there is no mark on the location or clear where it's not below anything. So we're able to learn a large number of games over a lot of different types. So we're able to learn board games, river crossing puzzles, grid puzzles, side swapping puzzles, block puzzles, marking and logic puzzles like Sudoku, as well as solitaire and card games. And there's a link I'll share at the end where you can look into these in more detail. But using these strategies, we're able to learn a large number of games and puzzles. We've seen this before, but we have also deployed this on a large different number of agent embodiments and task environments, including internally simulated ones and robotic ones, such as we can learn a lot of different terms. So you saw an example where I learned clear and also where I learned captured, but I can learn nouns, such as if an object is a blue block then is a toad. Nouns that act like functions, like if a block is on a boat, then the block is a passenger of the boat. State verbs, like if you can move a piece onto a location and the piece is attacking the location. Adjectives, like if a bank is below the boat, then it is the current bank. We can learn comparative adjectives like smaller, superlative adjectives like largest, and prepositions like adjacent. And it's not to say that we wouldn't expect that some of these would be predefined, but we have the power to learn context-specific definitions of these terms. And this allows us from a basic set of primitives where we have some primitive verbs, prepositions, adjectives, and nouns to learn a large number of new terms by just getting definitions. Where I'm showing some experimental results that we did. So this is an experiment where we generated permutations of 17 different games. So here there's just 3,000 permutations. And so the learning order is basically saying, when is it in that order of 17 games? So at the very beginning, basically, it can't benefit from any transfer. So this is specifically looking at tic-tac-toe and the number of words it takes to teach. And so as we go further to the right, it has a chance that, it might be after Three Men's Morris, which is very similar to tic-tac-toe. So it could benefit from transfer and take fewer words to teach. We can explode this out to the other 17 games. And so we can see that in all cases, we're benefiting from transfer, even in cases where there isn't a lot of concepts that can transfer just because the game is
James, you have 3 minutes left.
Thank you, Peter. We repeated this experiment later on with 40 different games. And so here we're not highlighting them separately, but just highlighting a few key examples. And so we can see in one case, Killer Sudoku, that it really benefits from transfer of knowledge, starting it up almost at 250 words to teach and ending somewhere close to like 60. So this is because between Sudoku and Ken-Ken, which are both in this list, it covers all of the rules for Killer Sudoku. So it's able to really benefit from that transfer. On the flip side, there's puzzles like Frogs and Toads and Blocks Worlds that don't share a lot of concepts, and so they don't benefit from transfer. Great, so nuggets and coals. Coal. So my PhD is finished, so that I figured that I put that on there for a nugget. And so we have a recursive method for learning task elements that supports hierarchical composition and transfer of knowledge. Can learn over 50 tasks in different settings, can disambiguate between many interpretations in ambiguous scenarios. There's a public archive of all the games and puzzles that we've learned, the world representations and the agent-teacher dialogues at umich.edu//JRKirk HCHI 2019. This was work done for an HCHI paper. So cold, the agent is slow when there are many objects to consider. It needs an attention mechanism of some sort. It's similar to what Aaron mentioned. The language for teaching is limited to very structured explicit statements. There's also a limited capability to repair incorrect knowledge. We're kind of assuming that your teaching examples are good. And we've still not explored many different tasks and domains. And so at that point, I will ask for questions.
Thanks, James. I see one question on the chat. It says from Keith Lambert is asking, these seem to be in perfect information environments. Can we apply these ideas to less tidy environments?
Yes. I think you could. It's not something that we've done. And I mean, I will, to clarify, they have been deployed in robotic environments, but we rely on having kind of a mid layer that gives, that gets rid of that noise and says, okay, here's where the block is. And it has these symbolic relationships. To kind of maybe get rid of that would be interesting. It's not something we've explored. We definitely have an ability to handle things that are unknown just by filling those gaps with being able to learn new terms. So that can help resolve when there's a disconnect between your representation and your task.
Great. Thanks a lot, James. Appreciate it. Our next speaker is Eula Schatz, talking about learning causal relationships. Go ahead, Eula.